We are going to play connect the dots. Maybe. There we go. Brandon, what are good numbers to play connect the dots with?
0.
A 0.
A 1.
A 1.
A 2.
Okay.
A -1 and a -2.
Yeah. Those are good, 5 good numbers. Especially with exponents, the larger you get, I mean, the bigger the numbers are going to be. So if you're squaring a number or cubing a number, plugging in that 3 or 4 or 5, then you have values that really aren't plottable. No space to plot them. So when you plug in an exponent, and I did say no calculator, so try not to get that calculator out. Use your wonderful brain. We have 2 to the -2. When you have a negative exponent, Chelsea, what does that do to your number?
It puts it as the denominator.
Yeah, so it takes 2 to the -2 and puts it in the denominator. Cut, you want to get a drink? Are you okay? Okay. So that exponent is now a positive 2 by placing it in the denominator. And then we have 1 over 2 squared, which is 1/4. So no calculator required. Just remember what happens to a negative exponent. The second one is 2 to the -1. Sometimes writing it down just till you see the pattern helps a little bit. 2 to the -1 is really 1 over 2 to the first, or a half. So Chelsea, anytime you plug a 0 in as an exponent, you always get out a 1. And then when you plug a 1 in this case we have a 2. When you plug a 2 in, we get a 4. So we have an intercept right here. And that intercept will be pretty common because you're plugging 0 in for x, and it's always a 1 that you get out. So now we have these ordered pairs. Brandon said plot the points. I know the numbers we're plotting are small because they're decimals. Just make sure that visually it looks like one point is slightly higher than the other, and your lead is way thinner than my marker tip, so that should be a little easier for you than it is for me. But they should look like they're increasing, those 2 1/2, 1/4. And then we go up to 2, up to 4. Play connect the dots. If something grows exponentially, it means the points are going to get increasingly further apart as your x value gets larger. They're going to go higher and higher up the y values. Because 2 cubed is 8, and then 2 to the 4th is 16, 2 to the 5th is 32, so the distance between the y values are just getting larger and larger because you're taking something as an exponent. I didn't connect the dots on the, well, I stopped connecting the dots. How do you think the graph looks on the left-hand side of the graph? Like, I didn't do anything over there. Virginia?
Is it skim across skim 0?
It does. It skims across, getting closer and closer and closer to 0. Virginia, can it ever be 0? No. So when you have a base of any number, 2, 3, 5, 7, 1, there's no way to get that number to become 0. Because you already have the number there. And whatever power you take, even if it was -100, it's still never going to be 0. So what happens in a graph? What's that called in the graph? Brendan?
A constraint.
A constraint. What else is it called?
An asymptote.
An asymptote. There is an asymptote right here on the x-axis. It is also a constraint. You could use that word too. But we have an asymptote on the x-axis because it will never touch a 0. That's like our boundary line. It won't go below it. It won't touch it. It's just going to skim right next to it. Questions? So if you look right next door, we switched this a little bit by making it a 3, but the key thing is to notice that there's a negative exponent. So our goal is to see what happens versus a positive x versus a negative x. And you can use those same 5 numbers. So remember, you're taking 3, and then the exponent is already negative, and you're plugging in a -2. So Michael, that really means you have,
3 squared,
which is
9.
9, yeah. So really we have 3 squared. Michael, 3 to the -1 is?
3.
3 to the 0?
1.
3 to the -1?
Is that 1/3?
It is. And then 3 to the -2.
1/9.
Good. So remember, negative exponent really means we have 1 over 3 squared, or 1/9. So you can kind of see that the numbers are opposite because of that negative exponent. In the one on the left, we started at 1/4 and we got larger. On the one on the right, we're starting large and the numbers end up decreasing. So in the graph, you should definitely see that difference. There's also an asymptote in this graph at 0 as well. So just because we have a negative exponent doesn't mean that the asymptote is shifting, changing, flipping. So rational functions aren't the only functions that have asymptotes. Exponential functions, can't speak, also have the asymptotes. They just have horizontal ones. No slant, no vertical. So I think there's a little summary underneath to kind of get us to look at the graph and think about the different parts of the graph that we've been working on. So Grace, what's the domain of the graph? For both of them? So the domain would be negative infinity to infinity. The range is 0 to infinity. And that's for y equals 2 to the x and y equals 3 to the negative x. So domain and range for each equation. How about the x-intercept, Libby? There isn't any. Yeah. Is there a y-intercept, Libby?
Yeah, it's 1.
Yeah, there is a y-intercept. Both of them have the value of 1 because when you plug in 0, you're going to get out the 1. So the y-intercept is 0, 1. And then we already talked about the horizontal asymptote. That's at y equals 0. So if you look at the two pictures, it asks increasing versus decreasing. Eris, is one of them increasing?
Yeah.
Which one? Yeah, the one on the left's increasing, so that means the one on the right's going down. So the increasing one is 2 to the x, the decreasing one is 3 to the negative x. So the negative exponent is what makes it decrease, makes it go down. So positive exponent increases, negative exponent decreases. And then the last two questions here, 1-to-1. We talked about things being 1-to-1 when we talked about chapter 1, working with functions. So functions were all about chapter 1. What's 1-to-1? Alex, do you remember?
There's one input for every output.
So are these functions 1-to-1? Yes. So horizontally, you're looking at the graph. And if there are 2 points on a horizontal line, then we would say it's many to 1. If there's 1 point where you draw a horizontal line of your graph, then we say it's 1-to-1. Alex, do you remember why we checked if functions were 1-to-1? So the vertical line test check to see if something is a function. Horizontal line test, Virginia checks to see if it has an inverse, right? And these do have inverses because the inverse is a log function. So that's kind of why log functions exist, unfortunately for all of you. But yes, these are both 1-to-1. A function that is 1-to-1 has an inverse. That's what it means for something to be 1-to-1. So yes, it goes through the graph horizontally 1 time, but also it means it has an inverse. And then is it continuous? Are they continuous? Yes. So that means they start on the left, they go on the right. Continuity starts from the left side of the graph and moves to the right. As long as you don't pick up your pencil and skip over a point, skip over a hole, then we say they're continuous. It's okay that it doesn't go down. As long as the graph starts on the left and continues to move to the right, they're continuous. So this is a yes here. We're going to skip this last part because there's no really way to summarize the points they contain. They both have points depending on the number, that base. So the base determines the y values. Any questions with those two graphs? Virginia?
This is really tough. Would it be continuous if it didn't skip over anything, but it wasn't negatively, it was like, if the domain was 0 to infinity, it would still be continuous?
Yes. Yeah. So the only way that it would not be continuous if some way that you could, like there would be an asymptote that goes through the graph vertically, or you ended up, like for some reason, having a hole in the graph, like it just stopped and then it skipped over. But with these functions, that does not happen. They're always continuous. So continuity is always from left to right. It's never looking like vertically. Other questions? So at the top of your page, which is at the very bottom of my screen, is this wonderful number that we learned last year. Besides the number I,
It's E.
it's E. Yeah, we talked about E last year. We're gonna only talk about it a little bit. Pretty much the fact that it still is an exponent, it's a base. So we could write E to the x, just like we can write 3 to the x. So it's considered an exponent. It gets used a lot in application problems. And last year we created the number E by taking $1 and trying to like compound it multiple times. So like we took it to the first power, the fourth power, the fifth power, the 10th power, and our goal was to see like how much, if we invested $1 after an infinite amount of days, how much money could we get out? And that there was a maximum amount of money, and that maximum amount of money, does anybody remember what that was? How much your dollar would be worth? It is 2 point something. So your $1, 67 years from now, is going to be worth $2.72 ish, and it won't ever be worth any more than that. But hey, you like more than doubled your dollar, almost tripled it. So that's the number E. But it's used in a lot of different applications. That's the one that if you're graphing it, you'll have to use your calculator. It's taking 2.718, squaring it, cubing it, taking it to the negative first. Like, without a calculator is kind of hard to do. So at the top, there are 4 different equations. Without graphing, we're going to see if we can describe the transformation. Brandon, a transformation is doing what to a graph?
Moving it.
Moving it or,
Changing it.
well, that is kind of moving it. Moving it or,
Dilation.
not dilation. Well, yes, dilation. We could dilate, make it, stretch it or shrink it. What other word? Flipping it, yeah. So shifting it, flipping it, yes, dilating it, making it stretch vertically or horizontally. So those would all be transformations. So
Flipping it is moving it.
that's true, yeah. I was looking for flip though, or reflect. Sorry, Brandon. Yes, you're right. Going back to chapter 1, we did a couple of sections just graphing random graphs and translating them, kind of knowing what happens in the graph based off of the way it's written. So now that we're talking about exponents, it's okay that it's an exponential form, it still moves the same way. So if we have y equals, or g of x equals 3 to the x plus 1, Chelsea, how does that graph translate? Yeah, so when it's with x, pretend there's parentheses around there. When we talked about translation, we said any function, doesn't matter what the form is, has that standard form of with the h and the k. When it's with x, it moves it left and right. When it's outside of the parentheses, outside of the exponent, outside of the function, that's the k value that moves it up or down. And since it's with x, it moves the left. It always moves the opposite direction, because really this is 3 and then x minus a negative 1. That's how we get that plus 1. So that negative 1 is really the part that's making it move. So then letter B, Kate, how's that one moving?
Would be down 2.
Yeah, that number, that negative 2 is outside. It's away from the x. So it doesn't affect x, it affects y. So this one goes down 2. Okay, so C and D are a little different because now they're just throwing in a negative sign. Sabrina, do you know what happens with letter C when there's a negative in front of the 3?
It's flipped on the x-axis.
Yeah, so this is a flip, or you could say reflection, but it's reflecting over the x-axis. Because when you have a negative in front of the 3, you're making the y's negative. That means you're going down below the x-axis. So even though the y's are becoming negative, you're actually flipping over the x to get underneath the x-axis. So that's why it's reflecting over the x-axis. And then the last one we actually graphed, this guy right here. So you can even see the difference from one to the other. This one is a reflection over the y-axis. And that's because you're making the x negative, which means now you're on that negative side of the vertical axis. So you're reflecting over the y-axis. questions with those. So without graphing it, without doing any work, just by looking at where the number is, you should be able to explain the transformation. Questions? So there are 3 properties that I thought were good ones to review. I think we talked about like 6 or 8 last year in Algebra 1. But these are 3 that are pretty commonly used. And we'll talk about these same properties with logs as well. So we have a to the x times a to the y. Chelsea, what's that have to go along with? What happens there?
It's a to the x plus
Right. So when you are multiplying and the base is the same, that's what that a is. So they're both 2's, they're both 3's, they're both 7's. The same base. You can really add the exponents. You're not multiplying the bases. The way you simplify that is by adding the exponents. And this works both ways. So you could start with something being added and you can actually split them apart into a multiplication problem in case you need that to solve a type of problem. So you can go on either side of that equal sign from one to the other. Letter B. Asia, if we have a to the x to the y.
Is it multiplied this one?
Yeah, this one's where the exponents get multiplied together. And if there are multiple exponents in the parentheses and everything's being like multiplied together, that just distributes to every exponent. So if I had a to the 4th times b to the 3rd times c to the 5th, that exponent would just multiply to every power in the problem. And then Alice, a to the x divided by a to the y
one.
is?
So it would be the x over y.
Right. Not quite.
Minus one.
So that's what it will look like if we wrote it as division. So then it would be a to the x minus y. So multiplication becomes addition. You're actually adding the exponents together. Division becomes subtraction because you're actually subtracting or canceling those exponents out. So if we had like a to the 4th divided by a squared, you could really say we have 4 a's and we have 2 a's. And you're like subtracting those 2 out. So you would have 2 left. So the question underneath is a little different. It says use properties of exponents, which we have above, to determine which functions, if any, are the same. So we have 3 functions given here, and our goal is to see are any of these the same. Without graphing it. Now yes, you can plug these in your calculator, and if you get one equation graphed and not 2, then obviously they're the same. But we're going to see if we can try and use some properties of exponents to determine if they are the same. So when you have numbers, numbers can be broken down into smaller bases. So the number 4, we have 4 to the x, just looking at this first problem here to kind of get you started. How can 4 be broken down to a smaller base, Brandon?
You could take the square root of it.
So how else, instead of saying take the square root of it, how else could you write 4?
2 squared.
4 is 2 squared. So 4 is 2 squared. So we're just rewriting the 4. Brandon, how could you rewrite 12?
2 times 6.
2 times 6, or besides 2 times 6, what else?
2 to the 3rd.
How about 4 times 3?
I was trying to get common.
Oh, well, but I am, because 4 is really
2 squared.
2 squared
Times
and times 3. Okay, good. There we go. I think that's what you were trying to do.
Yeah, I just kind of forgot.
That like magically changed colors without me picking up my pen. I really did just write in red. I swear I didn't pick up a pen. It's magic. Look, see? Now it's back because I put it back. Nobody else saw that? I had 2 colors in my hand. It magically switched colors. I'm crazy. Okay, so we changed the number to a base, the smallest base. And right now we have 2 to the 2x. That's really 4x. But we changed the 4 to 2 squared. The x is outside. Asia said we could multiply them together so that we have 2 to the 2x. And then we have 4 times 3. Well, 4 is really 2 squared, but 3 can't be broken down. Because these bases are the same, and there's a plus sign in here, can you combine them together? No, because our properties say You have to have a multiplication with the same bases, or they all have to already be in exponent form to be added together. So this is as far as you can break this problem down. This is still equal to f of x, but does it look like either of the two options that are up here? No. So f of x probably is not the correct answer. That could be changed to g of x or h of x. I'm going to skip g of x, and I want you to look at h of x and try and break that one down to a smaller base. So that's the goal here. Can you take the big numbers and break it down to its smallest possible base? So think 64 is fairly big. Your goal is to try and break down 64 and start easy. Make a little factor tree if you need to. So 64 can be broken down into what two numbers, Alice? Any two numbers.
2 and 32.
Okay, 2 and 32. 32 can be broken into?
4 and
4 can be broken into?
2 and 2.
And 8 can be broken into?
2 and 4.
2 and 4. Which can then be broken into?
2 and 2.
2 and 2. How many 2's do we have up here? 6. So 64 is really 2 to the 6th. Like that's a way to break something down algebraically without using your calculator. Anybody still has that power sheet from last year? I don't know if any of you still have it. We had that huge power sheet where we listed things. That's kind of coming back into this stuff here, so those exponents. So 64 is 2 to the 6th because there are 1, 2, 3, 4, 5, 6 different 2's up here. So that's prime factorization, breaking something down. The 4 we said is 2 squared. So I'm just changing 4. And then if I rewrite this, we have 2 to the 6th and then 2 to the 2x. Just bumping this x in with the 2. How can you write that? Libby, what do you think? How could we write that?
I wrote it as 2 and then as an exponent 6 plus 2x.
And why can you do that?
Because they have the same base.
They have the same base. So the base is 2, the base is 2. If the base is the same and you're multiplying them together, that's the property A, you can add the exponents. So Libby, what is h of x equal to?
2 and 6. Oh wait.
Which other function is it equal to? These guys are actually the same exact function. They're just written differently. So the first one is written, and it's like the large number expanded. So 64 times 4 to the x. The second one is written as a single base with an exponent. That single base is 2 to the 6 plus 2x, but it really means 64 times 4 to the x. So kind of just like breaking it down differently into this is a single base here with an exponent as opposed to having the other initial expanded form. Questions? You can do the same thing up here, like you could work this the same way. You could say you have 2 to the 2x. The addition sign means I can separate it into its second base. And this would then be like pulling it apart and separating it. So 2 to the 2x is 4, and then we just said that becomes 64. So either way you want to work through the problem, but it's kind of like changing it to try and break it down into a single base with an exponent. Questions? So I think that's like the most thought-provoking problem, just a little different. If you look at the last 4, you can actually plug these in your calculator. So somebody who has a calculator out, I know all of you don't have one on your desk. Chelsea, what is 2 to the negative pi?
0.113.
Yeah, it says 3 decimal places, so 0.113. Kate, you also have a calculator. What'd you just type in?
Yes.
How about e to the negative 1, Kate?
0.368.
368. We know e to the first, we just said that at the top of the page, 2.718. And then 2 to the negative 3.1, Chelsea? 117. So, if you flip the page in the packet, I don't think I have this up here right now. I'm going to pass out some graph paper, but if you look at this page, the goal is for you to kind of see how asymptotes and intercepts change based off of the numbers that are being applied into the function. There are 4 questions on the front of the page and there are 4 on the back. The ones on the back are way more interesting than the ones on the front. So you're gonna make a little t-shirt with at least 3 points. You're gonna graph it. If you'd like to graph it on there, you can. But then you'll have to make little tick marks. You have to make a vertical and a horizontal axis. So you can feel free to just graph it on graph paper. So your goal would be to then kind of look at the graph and say the asymptotes are here, the intercepts are in this location. There's a domain range, so you're kind of just interpreting graphs. Need another one.
Well, no, we just need everybody just.
No, because that's 4, there's 3 problems that you're graphing with 37, 39, 41. And then there's 8 from this. There's 12. You're good, you'll have enough. And then there are a couple of problems in the book. So there's 3 graphing problems in the book. 17 to 20 are matching problems where you're given a graph, you're matching it. And then the back end of that, 57, 61, 73, 80. I think 80 is an application problem. The other 3 are not graphing, just kind of asking you to look at a problem if you've got questions. Tomorrow will be way more involved, just giving you a heads up. Tomorrow we're talking about logs, graphing logs, using properties of logs. No, the common log, natural, common, any kind of log.
I saw it online, I was like,